Okay, perfect. Yes, yes. Thank you so much.
All of these photographs, they look like Hubble, but in fact, every one of them was taken by our members. And they are incredible. There's more where these came from. In addition, there are these little flag pins that Tim brought in right here. So sometime over the course of the evening, help yourself to one. Also, I was told that how many folks have seen the International Space Station pass over? Okay, just a few of you. We get a chance to do that today because at 10:15 the International Space Station will be passing over, and it's going to be very, very bright. And we arranged that just for you. That's right. Yeah, took some arm twisting. Our speaker will use their influence. Let's see. Oh, we're all volunteers. Yes. Live. Okay, we're all volunteers. If you enjoyed your visit and you wish to donate, there's a means of doing that near the door. And I welcome everyone. And tonight's, I'll get right to the speaker. Tonight's speaker is Elaine Stewart, Aerospace Engineer from NASA's Goddard Space Flight Center. She'll be discussing her efforts as a Contamination Control Engineer for the James Webb Telescope. Additionally, Elaine will introduce the Roman, I didn't really know that that was happening. So that's
Yes.
going to be great.
Yes.
The Roman Space Telescope slated to launch in 2027. So everyone, please welcome our speaker.
Thank you. Thank you so much. I'm very excited to be here tonight. I'm going to be again talking about the James Webb Space Telescope, launched in December of 2021. I was lucky enough to be there, so I'll talk about the launch campaign, and then I'll talk about the project that I work on now, the Roman Space Telescope. So I'll take questions at the end. I will be here the entire evening with my parents. Feel free to stay as late as you want. I would love to talk to you, but let's get into it. So this first photo here is actually from 2017, and this is right before the telescope left Greenbelt, Maryland, and we were on our way to Johnson Space Center in Houston. So I'll talk a little bit more about how this telescope has been an international collaboration and traveled internationally before going to space. So here's a little bit about me. I should probably start with the fact that I grew up in New Jersey, actually near Princeton, and I attended the University of Delaware to pursue my degree in chemical engineering. I was lucky enough to actually have an internship with NASA starting the summer right after my freshman year. So I went to the Kennedy Space Center, and I spent the summer actually working on a lunar mission that's going to look at what constituents are in the lunar soil. It's very important in terms of going back to the moon. We need to know what's there so that we can sustain our presence in space. So this mission is actually looking at, how much water is there? Could we use components to make fuel on the moon? And this is all part of the Artemis missions. If you heard, we're having a return to the moon. So it's very, very exciting to work on that mission. This photo here is actually me walking through the doors that many astronauts have walked through and out of on their way to the Astrovan before going on launches with shuttle. And there's all stickers from the different missions. And then this photo over on the right is actually, it's called the VAB. It's the Vehicle Assembly Building, where they actually stack and build the rockets at Kennedy. So I had such a fantastic experience that was funded by the Delaware Space Grant that I then knew I wanted to work at NASA for my career. So I was lucky enough to actually be accepted into NASA's Pathways program. It's a co-op program, so I was able to start and continue while I was still pursuing my degree at Delaware. And I was working at Goddard Space Flight Center, where I still am. So this is in Maryland. It's actually not too far away from here. And some people don't know that it's so close by. The Hubble Space Telescope was built at Goddard. They actually did practice for the Hubble servicing missions there. The James Webb Space Telescope was built at Goddard, and we have many incredible missions that are being built there every day. Here's a photo of me. Now, my background for aerospace is in contamination control. So contamination control is actually making sure that all of these very sensitive surfaces like the mirrors and the instruments are as clean as possible, because we want to get the best science as possible once we launch. So this is what I look like most days when I'm at work. All flight hardware is built in a clean room. There are different sensitivity levels depending on what type of hardware you're working with, but usually you're in a bunny suit, so you're covered. The only part that you see is this much, and you need to do that to keep the hardware safe while you're actually working on it. So contamination control engineering involves material science, chemistry, thermal engineering, but the whole goal is just to make sure we get the best science possible once we actually do launch. So let's talk about Webb. Webb was designed to look at 4 different areas specifically. What was the first light that occurred after the Big Bang? How are galaxies formed? We have a lot to learn about the formation of them. How are stars formed, and what does star death look like, the life cycle of stars and galaxies? And then what other planets have similar characteristics to Earth? So this is just kind of showing, there have been a couple of other missions that have also contributed to these fields of interest. There's one mission that I like to point out, COBE here. This looked at the cosmic background radiation, and the project scientist from COBE, Dr. John Mather, he actually won a Nobel Prize for the work that COBE accomplished, and he became the project scientist for Webb. So he is using, the work that he has done to apply to Webb. We also have Hubble, and this is showing the time frame that Hubble is looking at, and Spitzer. But here you see Webb. We have the cosmic dark zone, and a lot to learn about it. So to make these observations, we needed the telescope to be very large. The optics were actually 6.5 meters. If you're familiar with Hubble, Hubble's mirror was only 2.2 meters, so it was almost 3 times the size of Hubble. And we needed that so that we could actually be able to observe the light from these very faint, very distant galaxies. So this is just a little depiction. You can think of starlight as rain, little rains of light particles. And to be able to gather more, we need a larger telescope. And so to do that and see those very faint signals, we needed the telescope to be very, very clean. So there were a lot of challenges. Now, I'll show you some more photos of Webb, but there wasn't any protection around the optics. It was an open architecture. So we had to be very careful through all of the steps, building the telescope, transporting it, the launch campaign. Every single thing was thought through so that we would make sure that the telescope operated as best as possible. And we had to move from one facility to the next. So hardware was built, actually all over the world, integrated in places like Maryland and California, tested in Texas, and then we eventually launched from French Guiana. So we had a lot of steps to go in between before we actually launched into space. And I think it's also really important to note that Webb, was very complicated. We have very big goals for Webb, and we're already achieving them. And it needed to be an origami telescope because of the large mirrors. The size that they developed to actually be able to look at some of that first light after the Big Bang couldn't fit in any of the rockets that existed. So they said, we still want to accomplish the science. We're going to work around it. And they actually call it now the origami telescope. I'll go through the deployment sequence, but they actually had to fold the mirrors. We have a sun shield that helps out with the thermal control of the telescope. They had to actually fold all of that and deploy it. So it was a feat of engineering to make this telescope actually fold up and then deploy in space. And there are a lot of advancements that were necessary to actually do this work. So this is just a couple of them. The micro shutters are used on one of our instruments called NIRCam that I'll talk about a little bit later. The back plane is what the mirrors are actually laid into. This is a very lightweight material, but also very sensitive. You can't impart loads on it, or else you'll basically affect the structural integrity of it. We have our lightweight cryogenic mirrors. They're made of beryllium with a gold plating on top of it. The sensing control we needed for our instruments, our detectors. The sun shield, which is the size of a tennis court, that was developed. There have been so many advances that were necessary to make Webb possible. And these are the instruments. So there are 4 different instruments that we have on Webb, and they all have different characteristics. So we have near-infrared, mid-infrared instruments, fine guidance sensor, and we use all these at different points depending on what we're observing at. And so since my background is in contamination engineering, I just wanted to briefly show you the thought that was put into the requirements. So we actually worked with the science team to make sure that they were going to be able to make the observations that they needed. And we look at contamination levels versus stray light. So if you have dust on the mirror, then that affects your image. You need to have a certain amount of throughput to actually be able to gather light from very distant targets. So I just have here, the importance that if you have dust particles, it'll create scatter, and we worked with the science team to make sure that we were actually able to meet their requirements. So this is the journey of Webb. This photo is where I showed you the first one with me pictured in it at Goddard Space Flight Center. This was building the optical telescope assembly. Now, we actually have facilities at Goddard to do environmental testing. So we need to make sure that after we build it, it's going to survive the launch and it's going to survive the conditions in space. So the main test that we perform on all of our missions before going to space is we have a vibrational test. We need to make sure it will survive the vibrations that it will experience during launch. We have an acoustic test. Need to make sure that it'll survive the sounds during launch. Thermal vacuum chamber test. And that's to make sure that it can operate at the temperatures it will experience while it's on orbit, which for Webb was very, very cold. We were at cryogenic temperatures, very cold. And so we performed all of those tests at Goddard. This photo is actually showing we're about to lift onto a shaker table. So they tested an X, Y, and Z axes, make sure that in every orientation the telescope can survive. And we have a little clean tent on it because it's not a clean area, so we maintained the cleanliness of it. Once we finished testing, we actually put it in a transporter, which is basically a mini clean room. It has humidity, temperature control, units to make sure that the air is filtered, and we flew it on a plane to go to Houston. So in Houston, we used their thermal vacuum chamber. The chamber that we have at Goddard was actually not large enough. We needed to go and use their chamber, which was used in the Apollo eras, to test our telescope. It was a 100-day test that was performed on the telescope. Hurricane Harvey happened while it was in test. We were prepared for it. We saved the hardware. It was a very, very successful test, and we made sure that we could actually align the mirrors during this test. We had a target that we were looking at to say, okay, let's, what if this is our galaxy we're trying to observe? Can we actually have the light follow the path it needs to? And will it survive and operate at these really cold cryogenic temperatures? Now, after it successfully passed its thermal test, we put it back in its mini clean room and we flew to California. So Northrop Grumman in California, they built this right here, which is our sun shield. It's the size of a tennis court when it's deployed, and it's 5 layers of mylar. There's actually around a 400 Kelvin difference between the bottom layer, which faces towards the sun, and the top layer near the telescope. It distributes the heat because if we are looking at, while we're looking at these targets, we need our instruments to be at very cold temperatures. We can't have the sun actually impacting the instruments while we're making these observations. So we have the sun shield to basically hide the sun from us so that we can look at these faint and distant targets. So we integrated on top of the sun shield and we became an observatory. So here you see this is what Webb looked like in its full assembly. And we did those same tests again. We did a vibrational test, we did an acoustic test, and we were then ready to go to the launch campaign. So at this point, now that we had assembled with the sun shield, we were too big. We couldn't fit it in a plane anymore. And we actually had to go on the Colibri, which is a big barge. It was loaded in California, and it traveled through the Panama Canal on around a 1.5 to 2 week trip to French Guiana. And this is just a photo of them unloading in French Guiana. So the town that we were located in and where ESA has a launch facility is called Kourou. And from there, we then went through the launch campaign and the launch. So this is what the launch site looks like. Now, there are a couple of different rockets that are actually launched from here. The Ariane 5 was the rocket that we were on for Webb. The Vega is another rocket that ESA launches, and the Soyuz is actually a Russian rocket. So there are a couple of different launch pads, but we were focused around the Ariane 5 area. And I'm going to show you now a video just describing a little bit of the efforts that we went through while we were at the launch campaign.
On November 29th, the Ariane 5 is transported to the Final Assembly Building, or BAF. Meanwhile, Webb's fueling operations went flawlessly. With its tanks pressurized with liquid death, Webb was loaded into its transport container to meet its rocket. Even its transporter container is a mobile clean room on wheels. In fact, we should take a moment to talk about how hard people work just to keep the environment around Webb insanely clean. Of course, keeping spacecraft clean is always a priority, which is why they're assembled in climate-controlled clean rooms and everyone wears those cute bunny suits. But when it comes to cleanliness, Webb is once again on a whole other level. Remember, the observatory has to be extremely sensitive to detect very faint infrared radiation. But that also makes it extremely sensitive to even the slightest contamination levels. For example, plastics can release hydrocarbons into the air, adhesives can release phthalates, and water in particular absorbs infrared radiation at 3.1 microns. That's a critical science-observing wavelength. So even tiny water droplets are a contaminant. Now, to be clear, a couple of contaminants here and there will not blind Webb or anything, but they will degrade its sensitivity. If that were to happen, then you'd have to take longer exposures to compensate. Longer exposures mean fewer observations over its mission lifetime, and fewer observations means a reduced science output. And that's why Webb has to be kept so ridiculously clean while still on the ground at all times. But even Webb's own design makes it prone to contamination. Traditional observatories like Hubble and Kepler enclose their telescopes inside tubes that are sealed while they're on the ground. And that goes a long way towards protecting its optical systems. But Webb needs to be much larger than Hubble while weighing only half as much. As a result, the telescope is largely exposed. And that's why NASA sent a crack team of contamination control engineers to help ESA and Arianespace prepare every facility in Kourou ahead of Webb's arrival. Not only was every surface in every room custom cleaned, but all of the facilities had to be modified as well. For example, NASA supplied 2 portable HEPA filter walls to control contamination levels near the spacecraft. Contamination engineers cleaned, covered, bagged, sealed, and even removed anything that couldn't meet Webb's cleanliness requirements. They turned every facility Webb visited, including the fueling station and the final assembly building, into state-of-the-art clean rooms. They even cleaned the living hell out of every surface near Webb each night after everyone else went home. If cleanliness is next to godliness, then these people are saints.
So I'll show you a bit of
On November 29th, the Ariane...
Pause really quick. Okay, so he was just talking about the filter walls. So in every clean room that you go into, they have what are called HEPA filters. They're high efficiency particulate air filters. And they're used, as a barrier. We want to make sure that any particles that are too large are not able to get into the clean room, and we can maintain the cleanliness. And Webb was the most sensitive mission that had gone through the facility here at Kourou. So we had to go through and make sure, everything was up to the standards for Webb. For each facility, we actually went in and we did inspections. If anything needed to be removed, it was removed. We put up the HEPA filters to make sure that the proper cleanliness levels were met. And this area right here is actually next to the fairings. So the fairing is the top of the rocket. There's one at the back, that's the Ariane 6 fairing, which is their next rocket that they're going to be launching very soon. And the Ariane 5 over on the right, that was our fairing. So the fairing has the field of view of the telescope. It goes right over the telescope, and it's the last surface that it sees. So after maintaining the proper cleanliness throughout all of the campaign and all of the mission, we had to make sure that that was also as clean as possible. So this was for the fairing. We actually did a cleaning of the fairing itself. This fairing was created by a company called Beyond Gravity in Switzerland. They cleaned it there. They actually shipped it clean to us, and we did a final inspection that involved NASA, ESA, CNES, which is the launch facility group at Kourou. And here you can see just how large the fairing is in comparison to the people. The photo on top is actually myself cleaning. The item that I'm cleaning is called FAP, or Fairing Acoustic Panel. And this is actually used to help kind of distribute, the sounds that occur during a rocket launch and absorb some of them. And this is another photo where you can actually see all those fairing acoustic panels. So we went through and made sure that the fairing itself was as clean as possible too. These are some other photos from the launch campaign. So this is myself. I'm using an air particle monitor to check and see what the counts are in a room before we use it to actually launder these garments here. This photo is from, if you watched the launch the day of, you will have seen this room. This is actually where both on the ESA and the NASA side, we have representatives to make sure we're all go for launch before it happens. And then this photo down here is of an Ariane 5 mock-up. So the rocket that we launched on, they had a large scale model of it so that you could see for comparison. And this was our actual rocket. So in the video it showed, but we actually had to develop a clean shower. We called it the air shower curtain, right around where the fairing went on top of, because if you can see here, the door rolls up all the way and you're exposed just to everything outside. It's a tropical environment in French Guiana. We had to make sure that we protected the telescope and the fairing itself all the way up until we rolled out to the launch pad. So this is basically, the equivalent of the vehicle assembly building in Kennedy at French Guiana. And then we successfully launched. So it was a Christmas Day launch, and I was so lucky to actually be there in person. It was an incredible experience to actually witness the launch happen. And the telescope was built as an international collaboration, and through the end of it, it was very essential to have NASA, ESA, the Canadian Space Agency all working together to make this possible. So this was the team that I was working with at the launch campaign, and just a small portion of them. There's a much larger group all together. And this is another photo where we're right in front of the Ariane 6 rocket, which you'll be seeing launches coming soon for that. So after we launched, it's actually really the start of the mission. We had a long duration where we launched in December, and it wasn't until July where we had the first images released. And that's because we first had to deploy the telescope. So they deployed some of the components on their way to L2, which is 1 million miles away. Again, we're sending this telescope, and it's currently stationed right now 1 million miles away at Lagrange Point 2. And these are all the steps that need to happen. So it was folded up, that origami telescope, to actually fit in the rocket. We had to first deploy the sun shield and tension it into those 5 layers so that we had protection against the heat and light from the sun. We then had to actually deploy the secondary mirror. So for the light to reflect, we need to have that secondary mirror. So it goes from the primary to the secondary and then into our instruments. We also had part of our primary mirror folded up. So you can see on either section, pieces of the primary mirror were folded back to fit into the rocket. And then this is what we looked like fully unfolded. And this is a photo. So you can see here's the sun. Here we are with Earth and the moon. And this is Lagrange Point 2. So the telescope is orbiting around Lagrange Point 2. We have the sun shield again positioned so that it protects us from the light and the heat of the sun so that we can make our observations. And this is how we talk to Webb. So there are actually ground stations that we use to communicate with Webb. And one of the main stations is in Baltimore, Maryland. It's called the Space Telescope Institute. And we have people there 24/7, and they're sending commands to Webb, looking at the data that we're getting back, using that for the the first images that you saw. It was all data that was collected here in Baltimore. And here are some of those first images. So this on top is showing a comparison of a couple of telescopes, the WISE telescope, Spitzer, and then JWST. And you can see that there's such an improvement due to the size of the telescope and the sensitivity of the instruments. Also, this is probably my favorite image, the Carina Nebula. You can see the resolution for Hubble versus Webb. We're able to see so many more of those stars that are being born and the stars that exist in those gas clouds. And this last one is of Stephan's quintet. And the first image that it shows right here is from Hubble. And then with Webb, we're actually able to peer past some of those dust clouds and observe the stars behind it. So we have many more exciting discoveries to come. Again, we're working in 4 main themes. So what was the first light? What did the early universe look like? How do galaxies change and evolve over time? What about stars? How are they born? What does star death look like? And then, are any other worlds similar to ours? We actually have the ability to look at the atmosphere around other worlds, and we've been able to analyze, what components are present there. So these are the 4 main science themes, but I wanted to add that the telescope also has time allocated for anyone to propose time to use the telescope. So some of the first images and some of the first work that they did was called the early release program. And anyone from around the world could propose time on it. So it'll be really exciting to see, what other targets we observe through programs like that. So now I'm going to talk a little bit about the Roman Space Telescope. I'm going to show first a video about it, and then I will tell you a bit more about why you should be very excited for 2027 when Roman launches.
The universe. For all we have learned about it, we have only just begun to reveal its secrets. What are dark matter and dark energy? How common are planetary arrangements like our own? And how many planets in our galaxy have the potential to harbor life? The Nancy Grace Roman Space Telescope will help answer these fundamental questions. Formerly known as WFIRST, the Roman Space Telescope is similar to Hubble, but with the benefit of 30 years of technological improvement. Each image from its wide-field instrument will have the depth and clarity of Hubble's best, but capture a sky area 100 times larger. The Roman Space Telescope will take the lead in exploring dark energy and dark matter. We only know they exist by their effects on observable matter, yet these 2 mysterious components make up 95% of the universe. The Roman Space Telescope's powerful 2.4-meter mirror and enormous field of view will also help us in the search for planets beyond our solar system, or exoplanets. It will watch for gravitational microlensing events, caused when a planet and its host star pass in front of a background star. Such events are rare, so catching them requires watching large swaths of the sky. To deepen its study of exoplanets, the Roman Space Telescope will house a beyond state-of-the-art coronagraph that will directly image and analyze Neptune-sized planets in orbits slightly larger than Earth's, a dramatic improvement over current capabilities. The Nancy Grace Roman Space Telescope will help us answer many of the biggest cosmic questions. Its wide-field view and coronagraph will complement missions like NASA's James Webb Space Telescope and transiting exoplanet survey satellite TESS. The Roman Space Telescope will be an indispensable part of space science during the next decade and beyond.
So the Roman Space Telescope is actually named for Nancy Grace Roman, who is deemed the mother of Hubble. She was a very prolific astronomer in her time, and we're honored to have the telescope named after her. And as you heard, we're looking at different targets. So this is going to be a very wide field view telescope. We're going to learn more about dark energy. And we're actually building a lot of the telescope in-house at Goddard Space Flight Center. We're going to integrate all the components together there. There are some pieces being built, like the telescope itself is being built at L3 Harris in Rochester. That's the part that I work mostly on. And then we have the wide field instrument is being built at Ball Aerospace in Colorado. I'm going to show you a photo from Greenbelt at Goddard that was taken just a few weeks ago to show our progress on the telescope. So this is the focal plane system. I actually brought some stickers for the Roman Space Telescope, and all of the stickers are inspired by this focal plane system. So these are actually the detectors in the heart of the telescope. There are 18 detectors here. They are very, very sensitive, and this is what we're going to actually use to get that 100 times larger field of view than Hubble. So we actually assembled all of this at Goddard, and it's now at Ball Aerospace to be integrated into the larger instrument. Okay, with that, I will be happy to take any questions. Again, I left some Roman stickers over here. There are also some Roman bookmarks, and I have some web stickers too. All right, thank you so much. Yes. Yes, absolutely. Okay, so one of the best descriptions that I've heard is that, Webb is 1,000,000 miles away, but it would be able to detect the heat of a bumblebee on the moon. So it is very, very sensitive. We're going to be looking in those infrared wavelengths, and they've actually, since we've increased the size of the mirrors and the technology of the instruments, the images that Hubble has taken versus Webb has taken, we're doing them in a fraction of a time because we've cut down the exposure time too. So we're looking at some very, very distant targets, but we have highly sensitive instruments. Yes. Yeah, so we're sending it out there because we want to look at these very distant targets. We have to be cognizant of the sun too, which is why we have the sun shield, and we have to do very specific positioning to make sure, any light from the sun would actually absolutely damage the instruments. We're calibrated to very, very faint targets. So we want to be as far out as possible so that we can kind of see as deep as possible. Yes. Yes. So we have looked at some of the planets. So I think there are some images that came out of Jupiter from Webb, and there are more plans to look at our planets too and see what else we can learn. There's some very, very high quality. I'll actually see if I can pull them up for you, but we have it. When we first released the images last year, it hasn't even been a year since we've started releasing images. It was July 12th of last year, and they released 5 images all at once, and there are new ones coming out sometimes weekly or even more frequently. So we have an Instagram page, we have a website that updates all of the images, and it is almost sometimes a daily occurrence. But we do plan to look at planets in our solar system too and learn more about them. How do we put it in space? Okay, that's an excellent question. So we have it in the rocket. The rocket is fueled, and they are able to actually launch the rocket quite far up into space from there. But we disconnect, and one of the key things to think about with spacecraft is fuel is very important. So they actually plan out the trajectory of where the rocket's going to go, where your mission's going to go. You have specific launch windows to make sure that you're going to end up in L2. And we hit the target for our launch, and then there was an excellent separation with the rocket that they actually conserved a lot more of the fuel than they had planned to with Webb. So sometimes you need to use fuel to course correct, but a lot of it has to do with the rocket launch and the propulsion that you get from that to actually get it to L2. We launch missions much further. There are some missions that are going to Europa, and those take years to get there. But we're able to successfully do that based off of planning. Sometimes there's, like gravity assists of different planets that we use to our advantage too. Yes. Yes. Okay. So it kind of depends on the component of the rockets. You know, there are some rockets, like SpaceX has rockets where they actually recover some of the components. There were like the shuttle missions, they actually recovered the shuttle itself. For the Ariane 5, I forget exactly where it landed, but there are components of that landed back in water. They track where all of the components are. They make sure the trajectory is safe, that there aren't any components that could land somewhere that they shouldn't be. And it actually took Webb a couple of weeks to get to L2. It was a short process, or a long process to actually get there, to be 1 million miles away. So it just depends. You know, there are some missions that are in what's called lower Earth orbit, and that's much closer to us. So it doesn't take them as long, like the ISS that we're going to see tonight, that is, you know, much closer to us than Webb is. So it just all depends where you're going in space and how long it'll take you to get there. Yeah, so that's an excellent question. So determining where to place it is very important, because you want to make sure that you'll be positioned properly for your science observations, and then also, yes, you're not interacting with any other telescope. So they have the ability to track where the telescope is. There are, you know, we actually have on the telescope itself, there are things called star trackers, and the telescope uses that to know where itself is. We have the ability to know its position and orientation because of some trackers that we have on it itself. And we're aware of all the other missions that are up there. So it's an involved process just to make sure that we're not going to be, you know, landing right on someone and we're positioned properly. L2 is very big. There right now it's not as crowded as some of the other places that we have in space. So there's a lot of room. And I asked someone from the Webb Telescope project, you know, are we going to run out of space at L2? And that's a long ways away. I'm told that there is plenty of space. The Nancy Grace Roman Telescope is also going to L2 actually. So they track where all of the telescopes are to make sure that we're positioned properly in there. Oh, I don't know the total number. I'm not actually sure the total number, but I know that there are definitely a few. It's a difficult L2 is a little difficult to get to, so a lot of telescopes are a bit closer than that. But I can check on the exact number. There aren't as many as lower Earth orbit where the ISS is. Go ahead. Well, I wish I was an astronaut. That would be incredible one day. I personally don't, but I will tell you that just a week ago, we had astronauts from the Artemis 2 mission come to Goddard. And these astronauts are actually going to go and they're going to do a slingshot around the moon. And they're going to use the module that they're planning on actually landing on the moon. So there were 4 astronauts that came to talk to us. One of the astronauts is named Christina Cook, and she actually worked at Goddard, where I work right now, and then became an astronaut. And she lived on the ISS for 11 months. She, at the time, was the female that had spent the longest amount of time in space. And she showed some incredible pictures. I thought the coolest ones that she showed were of Earth at night. So she actually pointed out where Baltimore was, where New Jersey was, based off of the lights. You can, you know, of course they know where they are geographically, and you could see where like 95 was. You could see where all the centralized lights were, but she said it was really amazing to go sit by the window and read. So I would love to go to space at some point, but I know the astronauts, they spend lots of time looking at Earth from there. What is Webb? Okay, so Webb is named after NASA administrator James Webb. So you'll hear some of the telescopes have more generic names, others are named after people. Usually they're people of significance. He worked during the Hubble era too, so it's named after a person. Okay, we got a question back here. Yeah.
What is L2? Is it something that they rotate around, or is it?
It's a Lagrange point. So it is. It's a little bit. Let me go back to the depiction over here. Okay, so it's what's known as a Lagrange point. I believe there are maybe 5 or 6 Lagrange points that exist, and what's actually great about it is that Webb doesn't need to use much fuel to stay. It's kind of like a, if you've ever heard of like 3-body problem or 2-body problem. So it kind of stays in this area at this Lagrange point. So there are very slight corrections that they need to do to keep it on its target of observation. But it's more stable than a lot of other orbits. And the benefit is that we can stay there for longer and do more science. So that's why they've picked Lagrange point too. Yes?
So I know Hubble been repaired some time back. So is it
Yes.
a possibility it can be fixed if that was something wrong?
So since it's 1 million miles away, we would have to get astronauts to be 1 million miles away. And we are working towards that. We're going back to the moon. We will go to Mars based off of our efforts with going to the moon. So right now, Webb would be very difficult to service. There may be an opportunity to refuel it. And that's a technology that there's another mission that is really exciting to watch out for. It's called OSAM-1. And it is going to lower Earth orbit and actually refueling a satellite. So there's a lot of development that is being put into how do we do robotic in-space servicing, because there's lots of fantastic technology that's in space, but fuel is a limiting factor. There are sometimes, the Hubble needed some work from the astronauts, and right now Webb is a little too far away. I think that if we had an issue, we would find a way, but it is working perfectly. There were over 300, they're called like single point failures because they're actuators that need to perfectly fire for Webb to deploy. And it is working perfectly, but 1 million miles away is a little difficult right now. I think that we will eventually be able to service there. Yes?
All right, so you've kept these mirrors incredibly clean all this time.
Yes.
How often is your work undone by micrometeorites while it's sitting out there?
Okay, thank you. That's an excellent question. So L2, luckily, since there isn't as many missions, there isn't as much to worry about breaking off into smaller pieces. There are still micrometeoroids. We actually had done an analysis for Webb where we track the micrometeoroids. So we try to understand the environment as much as possible. We actually even have the ability to do high impact velocity testing at, it's called White Sands facility in New Mexico. So they tried to analyze how many micrometeoroids we would expect, what would happen to the mirrors if they were impacted, and we did have some impacts from micrometeoroids. So what they did is they actually used, it's called phasing, and they used that on the mirrors to try and understand, where was the impact, how big was the impact. And the mirrors are so large, and luckily we kept them so clean, that there is a lot of margin. So those impacts that happened and future ones that possibly could happen won't impact the science. They're basically, little areas. This one, the ones that happened and we discussed were actually already kind of blocked by the secondary mirror struts. So there are some areas of the telescope that are kind of already impeded by a different piece of hardware, but we're always monitoring it. They did expect that would happen, and they're kind of prepared, and we kept it as clean as possible just so that we don't have too high of an impact from them.
Elaine, I seem to recall that when the sunshade was
Yes.
tested out in California, there was a significant problem that happened. I think that delayed it a year. Can you speak to that at all?
Yeah, so as you can imagine, I showed one slide that doesn't even scratch the surface of how many new technologies needed to be developed. You run into problems sometimes when you're testing. There was some issues that needed to be resolved after acoustic testing, and the sun shield, I found it to be very, very challenging because something that I learned while getting into aerospace is that you need to test everything like you're in space, but you're here on Earth, so there's gravity. You have to offload all of the flight hardware while you're deploying it. And so the sun shield, I think that there were a lot of challenges with basically offloading the sun shield so that there was no gravity so that you could make sure it would operate properly in space. And the sun shield itself was like very thin, like micron-sized layers. It had kind of spoolie systems. When you go up and see the telescope, you'll see the wires moving as they rotate the dome. They had spoolie systems to basically, tension out the sun shield. So there were lots of complicated technologies. And again, since we couldn't service it, we needed to make sure that it would operate perfectly when it deployed and we actually got to space. So we needed to correct everything and make absolutely positive.
One bit of trivia. Do you know what part was manufactured here in New Jersey?
Ooh, I should know this.
You don't know?
No, let me think about it. I know a part that was manufactured in Delaware. Which part was manufactured in New Jersey?
It actually wasn't manufactured. The gold coating was put on
Oh.
here at a facility in Moorestown, New Jersey.
Excellent. Wow. That's fantastic.
They had a spray coating.
Oh,
facility. I
excellent.
think it's microns thin.
Yes, very, very thin, very thin. Oh, okay, that's excellent to hear. I know there is some depiction where it shows like all of the different components, whether it was a process, and you look at the map and all over the place contributed to Webb to make it successful. How is it like in space? Wow. Well, it's very cold. Now, the astronauts, when they go out on their spacewalks, they have to wear protective suits. So they wear protective astronaut suits so that they can still breathe properly. They monitor the oxygen levels. Depending on where you are, there's radiation you need to be very careful of. So for our astronauts that are going to the moon, they have very specialized spacesuits that they're wearing. Something that I worked on while I was at the University of Delaware was improving the fabrics for the spacesuit technology. We applied a shear thickening fluid so that when you impacted it, it actually had resistance to that to make sure that if there was micrometeoroids or dust, or if you had a tool that punctured the suit, that it would still protect the astronaut and make sure that the fabric, wouldn't rip. So there are a lot of protections that you need to take when you're a human in space to make sure that you're safe and able to work and live in space. Okay. Yes.
Any specific reason you guys are shipping all the way to French Guiana for launch?
Yes, so we actually had a couple of colleagues that went on the boat with the telescope. Now, they were monitoring 24/7 the temperature, the humidity. We actually have shock sensors. They're called that. We have accelerometers that are on the telescope, and you look at that just to see what kind of loads is the telescope experiencing, because you want to understand if they're what that looks like and if there are any concerns for that. So we had people that were right there in case there was a problem that they could work on it. The transportation unit was actually built in Ohio. We tested it. It was used for the various moves from Maryland to Texas to California, and then to French Guiana. So at that point, we had already done a lot of testing on it, but we had people there just in case anything happened to make sure that it was still under the right conditions. Where's the Webb's orbit? Okay, so it's 1 million miles away. It's very, very far away. And this is what it looks like. So this is us. We're here with Earth. There's the moon. And then we're actually 1 million miles away from Earth, all the way out there with Webb.
Can you talk about the surface of the mirrors that are on the Webb versus the Roman?
Yes. Okay. So the Webb, Webb has beryllium mirrors with a gold coating, and the mirrors for the Roman Space Telescope is actually a glass substrate, and it's a silver coating that's applied on top of it. So there are different coatings. The Webb mirror is around 3 times larger than the Roman telescope mirror, and they're different sensitivities. So we have different cleaning procedures, different kinds of chemicals that we limit for use in the clean room, just to make sure that we're keeping those optics in the best condition possible. And I will say, the flight optics, you ideally would not touch them at all. If you have to clean them, then there are very specific procedures you use. But we have samples. We have like 1 or 2 inch samples that track with the optics, so that we can see when they've been in the same environment, if there's any change that we need to be concerned about. And we do inspections of the flight hardware. We have maps showing if there's anything to note, and we go back and check it again. So it's a very, very involved process to keep track on those optics and keep them in the best shape possible. Okay. Yes, thank you so much.